Hello everyone. In this recording, we try to merge the three separate parts that we previously generated for solving the hiking tree problem together and exactly follow what we had in this pseudocode on the exhaustive search. So this pseudocode, what it does is uh, have this big uh, uh, this large loop here that go through each of the possible solution, and for each of them see if this is if that solution is feasible solution, and if it was a feasible solution, then we see if it is better than the best solution that we had so far or not. So the difference is that if you remember, in those three separate parts that we have, in the first part we first generate all the possible solutions, then and store them in a list. In the next step, we go through that list of possible solutions and check if they are feasible or not. And finally, for the feasible ones, we calculated the objective function and choose the best among them. So the difference is that every time that we here in the pseudocode generate a possible solution, at, at, we test if it is possible, and then we compare it with the best uh, solution that we had so far, and uh, store it or not, and then go to the next possible solution and the next one till we um, evaluate all the possible solutions. So to do that, we go to our Colab, and I will call this hiking tree merge. So as we know so far, we need to either manually import them or ask the user to give us his or her problems parameter. So the same as what we did in those separate parts, we are going to use the input function to ask the user to give us his or her parameters. So far we ask about the number of items, how many items does the user have, about the weight of the list of the weights, the list of the values, and the capacity of the knapsack. So we get those those inputs, those parameters from the user, and then we start merging those three parts. So first of all, we need an initial solution. And as we see, we have started from a list of zeros. In this case, we do the same too. So the initial solution is a list of zeros based on how many items we have. We are going to regenerate that solution. And then because based on what we had in the pseudocode, so we in this for loop, every time that we generate a solution, a possible solution, we need to check the feasibility, and if it was feasible, we need to compare the objective value with the optimum that we had so far. Therefore, we need to define those variables outside of that loop, as also we can see that in our pseudocode. So we try to define those variables. So we have best value, which we could, as you can see in the pseudocode, it was negative infinity, so we can use any negative number here. Let's say -1, and best solution is none based on what we had previously. So this is nothing. So we don't know what is the best solution is, so it's nothing. Okay? This none actually means nothing. And then we should go to our loop for generating possible solutions. So this is our loop that we saw previously, that we used for generating the possible solutions. So every time that we generate a solution, because now we are merging them, we have to calculate its total weight, which is the summation of the weight of the items in that combination or in that possible solution. And also we need to have its total value if it was a feasible solution. So we need to define two more variables here for each possible solutions. And so we define solution weight equal to 0, and also solution value, which is also equal to 0. And so every time that we have a new solution, a new possible solution, we make them 0 again in this for loop to make sure that we actually calculate those values for that specific solution. And we have this one in case that the solution weight is a valid value, then we use the solution value to check to calculate its objective function. Now that we have our solution, now it is time for us to see if the solution, in this case our initial solution, is feasible or not. So we go back to first we need to calculate its total weight. And for total weight, we need a for loop. We go through each element and we calculate that multiplication, if you remember from the second part of the code. So what we did here is that we have the total value equals the total, sorry, this is not the total value. This is the total weight or the solution weight. This is not the total value. Sorry. This is the solution weight. Is the solution weight. Why I use this one? Solution weight. So we have the solution weight equal to 0. Then for each item, we update the value of the solution weight. How we update it? We use its previous value and we add that multiplication that we had previously, which is the item weight based on the user's input multiplied by its corresponding item in the solution that we have, which is the solution in this part. So so the solution weight is going to be what we need for checking the feasibility of the solution. So after calculating the total weight, we use an if statement to see if the total, the solution weight is less than or equal to the capacity or not. So if the solution weight is less than or equal to the capacity, it means that this solution is a feasible solution. So what should we do for a feasible solution? We have to go, we should go and calculate its objective function. So for that, if you remember from the third part, we need another for loop. So we could say for k in range of n, we go through all the elements of the list of the solution for k in range. Solution value this time is the solution value, and how we update this one, the same as what we had here. So I'm just going to copy paste this one. This time, instead of item weight, we need the item value. And also the iteration here is k, not j anymore. So I replace them with those j's with k here. So we calculate the solution weight. We check if it is less than or equal to the capacity that we have. And then if this solution, if this statement value was true, then we go through this part and then we calculate the solution value of that feasible solution, that we realize that, okay, that possible solution actually is a feasible solution. Then we calculate its objective function, which is the solution value. And then we need to see if this new feasible solution is better than what we had so far or not. So after calculating the solution value, we need to compare it with what we have as the best value. So here we said if the solution value is greater than the best that we had so far, is the best value here. Best value, what we need to do is to replace those values. So the solution value is going to be, sorry, the best solution is going to be the solution value, and the best value will be, sorry, the best value is going to be the solution value, and this solution is going to be solution itself. Okay, and then when we have this one, we are done. So we are checking everything, and what we need to do is to, out of this for loop, we go for the next solution. So here is the part that we need to generate the next possible solution. So we can say for, let's say, t in range of n -1 to -1, and this step is also -1 if solution t is equal to 0, then we need to change it. So solution t will become 1, sorry, will become 1, have 2 again. And because now we have a new feasible solution, we break, and we get us, this break helps us to get out of this for loop, and we go to the next iteration here. So we have a new possible solution. Using this break, we are out of this for loop. We go back to this for loop, our outer loop, and we try to do the same thing for this new generated possible solution. And if that item is not equal to 0, then we make it 0. So solution t is going to be 0. When we had all of this, we need to get out of that outer loop, and we need to print our solution. So print, we can say best value is, and then we can use comma and have the variable here. So it's going to print us best value, or we can use the best value is, and here we have our variable, which in this case is best value. We can also say print the best solution. So the best, let's say, selection is, and we have our let's say best solution. So let's see if this Lux works properly. So we run it and see what will happen. So it's asking for how many items do we have. So we had 6 items, and so the weight of the item is this part, so 543262, 543262, and now it's asking for the item's value, which is 10.86.594, 10.86.594. And finally, what is the capacity, which I think it was 15. And yes, the capacity is 15. So, yep, we have an error here. And the error is item weight. Let me mistake item. Yeah, I have a typo here. Sorry, item weight has an E. And now it is correct. Okay, so let's run it again. 6. Item weight is, what was it, 543262. the weight was I think 10, 8, 6, 5, 9, 4, and the capacity was 15. Okay, so here is the solution. The best value is 29, but the best solution is this one. Okay, now here is the problem that actually one of you asked today, is that when you have the best solution here, so sorry, when you want to store the best solution, this should be solution dot copy. So in this case, you are going to have the actual solution here, not the reference of the solution. So let's run it again. And again, we had 6 items, 5, 4, 3, 2, 6, 2, 10, 8, 6, 5, 9, 4, and 15. Here is the thing. So the objective function, the best value is 29, and the best selection is first, second, third, and fourth item. So we choose those 4 items, and this is the combination that we want. So here is the recording for merging those separate 3 parts that we had so far, and I hope you enjoyed this video. Thank you.